You ready? Here we go. I'm calling these less important expansions. I could give you a more deceptive title, but it's true. These are less important expansions, which is why some of you have been asking me questions about this. You're like, oh, sir, do I need to use this? Do I need to remember this? The answer is no, because they're less important, and I'll be justifying why that is in a second. So the first kind of less important expansion is the half-angle results. Half-angle result. Okay, what am I talking about? We've already seen double angle, right? So that's when you've got something like, say, sine 2 theta. Let's see how your memory's going. What's the expansion for sine 2 theta? 2, starts with a 2. And then sine, a plus b is the mixed up one, right? Sines and coses together. So that's why you get sine theta, cos theta. Okay, right. In the same way, you've got your double angle result for cos 2 theta. Okay, which is, it's like the Pythagorean identity. Instead of cos squared plus sine squared, it's minus. Good. Okay, now, just keep your mind on that for a second because we're going to use this result in a minute to get these half-angle results. What do I mean by half-angle results? Well, if these are double angles, I'm making twice the angle, okay? Half-angle results are these. Sine theta on 2, cos of theta on 2, and tan of theta on 2. Okay, what are these in terms of the regular old single theta expressions that we're familiar with? Okay. So, where you get, we'll do sine and cos first, and I'll get you guys to prove tan later on your own because it's a little trickier. They come from mainly this expansion here, okay, that's why this is important. If you remember, there were two other ways to write the cos 2 theta expansion, okay? And they were based on the fact that we can swap out these cos squareds and sine squareds for sine squareds and cos squareds, depending on which one, right? So, let's take this, and remember that we can write it in two different ways, okay? I can say cos 2 theta is equal to, first, let's replace the cos squared with, what can I replace cos squared with? 1 minus sine squared, good. So, that'll be 1 minus sine squared, then another minus sine squared, hence, 1 minus 2 sine squared, okay? You can use the same logic and you'll get cos 2 theta is equal to 2 cos squared theta minus 1 if you replace the sine squared instead. Now, where does the half angle business come in? So that you're not too confused, let's just introduce another pronumeral. Let's have alpha, let that equal 2 theta. Which implies that just 1 theta will be alpha on 2. Is that okay? So how does it apply to these two identities? Well, my 2 theta here will become an alpha, and my 1 theta here will become alpha on 2. This is where I'm getting to my half-angle results, right? So I've got 1 minus 2 sine squared alpha on 2. Okay. So now if I want a half-angle result, for instance, for sine, I just need to rearrange and make sine alpha on 2 the subject. Does that make sense? So I guess I will, let's see, let's get these two to swap sides. So I'll have 2 sine squared on this side. I'll have 1 minus cos on that side. So I want to divide by 2, then take the square root. Is that okay? Divide by 2. And take the square root. Ta-da! Same logic applies over here. After you get down through these lines of work, you should be able to say that cos of alpha on 2, after you make your substitution, will be, can anyone guess? How's it going to be different?
1 plus cos alpha on 2 x square root.
So you can check out your numbers online. Now, I said to you I was going to ask you to prove this on your own, which I will, okay? There's a couple of different ways you can go about it, right? You could use this same approach, and you could try and rewrite your tan 2 alpha, your double angle result, in terms of single alphas, right? Or you can say tan of theta on 2 is sine theta 2 on cos theta on 2, and see how it simplifies out, okay? So that's something I want you to think about. But that's enough. These two results here, they're the half-angle results for sine and cos. Now, we don't learn them because they turn out to be not that useful. This is what I mean by less important, okay? When you're doing real maths and like working with angles and functions, they don't come up very much. Yeah.
You know how you've rooted it for like square root?
Mm.
Did you plus minus?
Good question. Okay, now, why would it be plus or minus? Think about this for a second. What would that indicate to you about the angles? When cos is negative, right, for instance, that means you've got an obtuse angle, okay, or a reflex angle, but not all the way up to the third quadrant, right? Fourth quadrant, I mean. Okay. So you're somewhere over there. So when you say it's negative that, you're implying something about the size of alpha on 2, something we don't actually know, okay? So just leaving it as positive opens up the possibility that it could actually be somewhere else, depending on what alpha is. But it's not saying, look, I'm slapping a minus sign on the front. It must be equal to this, okay? So in terms of identities, this is what we use. Okay. Good question. Okay, so there's the half angle results. You don't need to memorize them. That's one of the reasons why I haven't addressed them, okay? But I'm showing you what they are now because they actually do appear on the sheet and you might be curious, okay? And they're not that hard to get.